percentage?
99 point something.
99.03. So you say a capacitor is said to be full at 5 time constants, which is equivalent to 99.0, is it 03? 33. So 99.33% of the source voltage. Is that right?
Yes, sir.
Yes, sir.
Great. Now we took some example in the class, and that was the last thing we solved before we left the class. So today we are going to talk about the discharging transient. So you remember that in class we said that if it is charging, what was the equation for voltage if it is charging? Yes, who remembers?
VC
VC is equal
is
to
equal to
Vs.
VS times 1 minus
1
E
minus E exponent negative
exponent
1
minus T on RC.
over RC.
Great. Then so this is when it's charging.
yes, sir.
Then when it is discharging, VCT is equal to
VC VS multiplying
E
exponent minus T on R.
RC.
RC. Okay, great.
That's the time constant.
Ali, you guys are serious. I'm so proud of you. Keep it up. Let's just keep it up like that. Oh. I mistakenly declined somebody an entrance into the group. So if you can place it in your group that he should rate, I was just pressing allow, then mistakenly I pressed decline. So you guys should put it in your group for me. I'm trying to share this question from my screen here. I seem to have a problem. I'm coming. Oh, who can get in touch with Rahanda? I have shared.
Sir,
Rahanda,
she's saying that
She has shared this.
she's saying her phone doesn't support this thing there Teams because of her iOS. So she's trying to get somebody's phone.
Oh, okay. I'm so sorry to hear that.
She shared it now. It's in the group now.
Oh, he's in the group now.
Yeah.
No, she's in the group. She has shared it already.
So when did she share it?
Just now.
Okay. So guys, I shared it with her on Monday, hoping that she would have given to you guys a long time ago, so you can revise and then go over, because I couldn't finish this thing this week. I doubt that we can finish it today, because we need to finish this week. I don't have to come back to it next week, so that we can do next thing another week, next week. So if she has shared it with you, you can open it. We are solving example 3.3. I'm going to take a screenshot and then put it on the screen so that we can all follow. You can open the slide and go to example 3.3. Okay. Who can read it for us? Yes.
So should I read?
Yes, please read it for me.
Abeka, are you reading? Oh, who's reading?
When a mechanical limit switch on a conveyor reaches its end of travel, the contract bounce 8 to 15 times in the first 5 milliseconds before settling. Each bounce sends a force switch close pull to the PLC digital input, potentially triggering multiple conveyor stops or counter increments. A debounce RC circuit, R equals 10 kilo ohms, C equals 10 mFarad, is wired across the switch input. When the switch opens or bounces, the capacitor discharges through R, maintaining stable high voltage at the PLC input for the duration of the bounce. The PLC only sees the bounce free settle signal. The capacitor is initially charged to 9 volts. Switch just opened. Find A, the capacitor voltage at T equals 5 milliseconds. B, whether the PLC input stays above the 5 volt logic high threshold during the bounce. C, the time for the capacitor to discharge 1 volt, the PLC input load threshold.
Okay, great. Thank you very much, Abeka. Do you understand what Abeka just read?
That wasn't me.
Oh, that wasn't
That
you.
was
Who read?
Gideon.
Gideon, great.
Gideon.
Oh, Gideon, Kafra, why send me the fancy ma Abeka.
Okay.
So do you understand? Please, who understands this question? Now, this is a problem we have in the industry. So in the industry, I was telling you in class the last time that we use PLCs to control all the systems there. And these PLCs, they use certain switches, right? Bottom. So for instance, you have a conveyor line that looks like this. Then it's programmed that automatically, like I was telling you in class, that automatically when a mass of an object sits on top of this place, there is a load cell here, right? That activates a switch. So usually all of these are switches. That mass is heavy. So when it falls on it, we have a spring-loaded switch, that looks much like this. So these ones are called contact switches. So if there is no object now, you know that for these kind of switches, there will be springs here so that it will stay open if there is no object. Now, when a mass settles on it, when a heavy mass falls upon this thing, each mass will overcome the spring constant. And so the switch would close like this. But this is where we have a problem. You know that there is still some potential energy in the spring. It's still loaded. It's still having some potential, some force, right? So it doesn't just close suddenly. It bounces because of the spring. It bounces. You see, when you close a spring, because there is energy in the spring, it still bounces up and down, right? Now, for some time, within some few milliseconds, you see the input going like this. It'll go high and low, on and off, on and off, on and off. Now, imagine we have a PLC and we've programmed the PLC that if it goes on, right? If the signal goes on, do something, then because of the spring, it is just going on and off, on and off, on and off, on and off. What do you think will happen? And it can go on and off about 100 times within some 2 milliseconds because of the spring. It's going very fast, on and off within 2 milliseconds. So let's say that we've programmed it that when it goes on, the motor should start, right? And this thing is going on and off about 100 times in a second. What happens? The motor will start and stop 100 times in a second. Please, you understand?
Yes, sir.
Yes, sir.
Wait, and that is a very, very dangerous thing. It can cause so much harm. In fact, the motor can't even burn because you are starting and stopping it instantaneously. It will cause so much harm. So what we do is that we use a capacitor. In this case, the capacitor is going to be used as a filter, right? We call it a debounce filter. So you see bounce because the bounce comes from the fact that because of the spring, it bounces. The switch stays, it doesn't fully close, it bounces before it finally settles. So we are going to use a debounce, stop it from bouncing, debounce filter. So in this case, we are going to use a capacitor as a debounce filter. And how does it look like? This is how a debounce filter looks like. We have a switch here. It's in the handout. So this is the switch over here that the load will come on top of. This switch is connected to a certain PLC input. Can you mute? Somebody is playing music in the background. Can you just mute yourself or okay. Okay, so when we have this, now this switch is connected to F, right? So pay attention closely, otherwise you get lost. Then we have a 24 volts line or the high, so that it provides all the energy, the PLC. So here is a PLC input. Is that right? So what happens is that when this switch closes, look at what happens here. So these are two types of switches that we use. Please pay attention closely, otherwise you will get lost in the bush and I can't find you back. This one is getting a little bit electrical, more technical. Let's look at what happens here. If I have a switch like this, we've done parallel connections. Then this one goes to ground. And I'm connecting this to an input. And this one is 24 volt. You can say that this voltage is already connected to high. Is that right? So the output, if I open it, so the switch is open. The switch here is open. So the voltage here at the output, when the switch is open, right? Switch and the voltage at the output. When the switch is open,
0.
it is at 24 volts. Please, do you understand? You can see that it's connected in parallel with the 24, so it's at 24 volts. Please, do we all agree? Now, see what happens when we close the switch. When this switch is closed, what happens? The input is shorted. So it looks something like this. We have 24 volts here. That goes to ground. Then it's supplying to a V out and we've shorted it. So will there, and here's 24 volts. So will there be a voltage output? If we close a switch, will there be a voltage output? Yes or no?
No.
Hello? Hello? If we close the switch, will there be a voltage output? Yes or no?
No.
No. The voltage output will be 0. Please, do we understand? So this kind of
Yes.
switch, we call them pull down switches. Because when you turn it on, the output is 0. When you open it, the output is high. So when you turn it on, you are pulling it down to 0. That's why we call them pull down. So this one is a pull down. But usually in the industry, to implement it well, we use resistors, right? So we have some kind of things we call pull down resistors. Is that right? Hello.
Hi.
Uh-huh. You guys seems lost. Is anyone here lost? Hello?
Hi.
Please, you understand what is going on here?
Yes, sir.
Yes,
Yes,
sir.
sir.
Right. So usually in the industry, this is how we implement it properly. If you don't put resistors there will be two huge currents flowing, when you short it. You see, when we short it, all of the 24 volts current will be passing through here to ground. Right, so it's going to cause a lot of problems. It's going to cause a lot of heating. The wires can melt. So because of that, we don't implement it this way. We actually have our 24 volts here. Then our switch comes here. Sorry, we connect this guy here to our output line. You need to be taking notes. Otherwise, you get lost. This thing is very important. Then we'll put a resistor here like this. Is that right? So that when we short this side, you know, um, um, so when we open it, the voltage connects here, and then when we short it, we will not get very huge currents going down towards the resistor. Please, do we understand?
Yes,
Okay,
sir.
so we have pull up and pull down resistors. Now let's come to this PLC circuit here. Now we've established that this is how it works. So this one is some kind of an inverted um, input, right? So how how do we implement the okay? So how do we implement the filtering? But this switch here is where the problem is. It closes repeatedly before it closes. So it will be opening and closing, and the motor will just be starting and stopping all the time. And we don't want that to happen. So what do? We will put a filter here. So we'll put a filter here like this. So that what happens is that the input to the PLC is not connected straight or directly to the 24-volt supply, but we are picking that input from across the capacitor, so that when you close it, the capacitor will charge. Then when it's quickly doing the closing and opening and closing, the capacitor is charged, right? So the PLC picks its input from the capacitor, and at the capacitor's output, it is very stable because we are charging and we are discharging. Please, do you understand what's going on here?
Yes, sir.
Great. So we use a debounce, a debounce capacitor to prevent this thing from happening. Please, do we understand?
Yes, sir.
Great. Now, let's go back to the question. The question is asking us that a debounce RC circuit of resistance 10 kilo ohm and 10 microfarad. So we are given that this is 10 microfarad and here is 10 kilo ohm. We need to find the time constant. So first of all, time constant. What will be the time constant? Yes, tau
RC.
is equal to RC. And what do we have? What will it be?
0.1 second.
No, let's always put it in milliseconds.
100.
Okay. 100
So 100
milliseconds.
milliseconds. Right. Then he says that the capacitor voltage at T is equal to 5 ms. So the switch bouncing back and forth occurs at within a period of 5 ms, right? 5 milliseconds. Now that time, will we be using the charging or the discharging transient?
Charging.
Why charging? So let's think about it carefully. He says that from the question, he says that the capacitor is initially charged to 9 volts at the moment the switch is opened. Right, the moment the switch is open, when you just closed it quickly charges to 9 volts because it's 24 volts. So it quickly charges to 9 volts, then the switch debounces, it opens, right? So when it's open, the capacitor will start to what? Discharge, isn't it?
Okay,
Yes,
yes, sir.
sir.
Yes, sir.
Great, great. So we will use the discharging circuit. So A VC at 5 ms will be equal to the 9 volts times E exponent -5 over what? 100. And what do we get?
8.5.
We have what?
8.561 volts.
561 volts. Okay, great. Please, do we understand? Now, in electronics, to turn on a PLC, an input signal that turns on a PLC is a 5-volt signal. Any signal greater than or equal to 5 volts signal will be able to turn. It is a high signal. We call it high. It means the device should turn on. So if we are having a 5, we are, if we are having an 8.56 volt signal, you see it's greater than 5, right? So the signal can turn on. Please, do we understand?
Yes,
Yes,
sir.
please.
Yeah. So during that 5 milliseconds bounce period, because of this capacitor, the PLC will still see only 8.561 volt. Please, do we get it?
Yes.
Yes, sir.
Great. Now, look at something tricky here. The circuit here told us that the the bouncing period stays for 5 milliseconds. So how do you design the circuit? You want to design it in such a way that in one time constant is very, very large than this debounce period. If you don't design it this way, what happens is that if it's bouncing in 5 milliseconds, so let's say that we have our time constant. We want it to be that one time constant is sufficiently large to take all of that bouncing. So if we don't design it that way, it would also be bouncing. The output of the capacitor will also be changing. It would also be bouncing. So you design the bounce capacitors in such a way that their um, their time constants are sufficiently larger than the time constant of the um, bounce duration. Please, we understand. Hello.
Yes, sir.
Hello.
Great, great. Now let's do question question B. So question B was whether the PLC input stays above the 5 voltage logic high threshold during the bounce. Great, so it does. Then C, the time for the capacitor to discharge to 1 volt. Now every logic um is having its own voltage thresholds. We call them logic levels. So for PLC, any voltage lower than 1 volt, at times it's 1.8 volts, right? But here the question is asking us to use 1 volt. So any voltage lower than 1 volt is a low volt, and the machine will turn off. It won't see it. So let's calculate how long it will stay when it turns on. That's at this 8.561 volts. How long will it take for it to decay to 1 volt when the PLC would see it as a low signal? Is that right? So let's do B. In B, what we have is V out is equal to VSE negative T over tau. Is that right? And we want to find T. So we know that V out here will be 1. Vs is 9. So E negative T over 100. Right? 100 ms. So whatever value we get will be in ms. Then we can divide through by 9, here by 9. And this is going to give, then we take ln on both sides. So we have negative T on 100 is equal to ln 1 on 9. Then we can say T is equal to negative 100 ln 1 on 9. And what will you get if you enter this in the calculator? Yes. Please, what's the answer?
219.72.
219.
19.72.
Okay, so it means that if we charge the capacitor full, if we put it on full charge and we charge it, it would stay for 0.2 seconds before it discharges to 1. And within that time, all that 5 millisecond thing has elapsed. Please, you understand? You see, the question said that a bouncing period lasts for 5 milliseconds, right? So if it takes 200 milliseconds before it turns low, then by the time it turns low, all that bouncing period has elapsed, and so we wouldn't see any bouncing period. The PLC inputs will see a very stable voltage. Please, do we get it? Do we understand?
Yes, sir.
Yes, sir. Yes.
Great. All right. Now, just like how resistors had inrush current, capacitors also have inrush current. Capacitors also have inrush current. So you remember inrush current in resistors? Have you forgotten? Okay, great. So capacitors also have inrush current. In fact, at times their inrush current is even higher than the inrush current of resistors. Way higher than the inrush current of resistors. How does this happen, and why does this happen in the industry? This is the reason why it happens. Let's say we have a circuit, right? That is, let's say we have a capacitor connected to a source, V source. Right. Now, look at what happens here. We know that current across a capacitor is C dV dt at time 0. Time t is equal to 0. The charges across this capacitor is 0, like there is no charge there, right? There is absolutely no charge across it. So this equation doesn't make sense. It doesn't work at time t is equal to 0 because there is no charge. The capacitor is empty. So what happens here is this. All the voltage of this source appears across this capacitor. Now we're saying that capacitors would gradually rise, but when you connect it to a source and it's 0, right, all that voltage appears across it. And it can't instantaneously say that instantly we are putting all that voltage across into the capacitor as charge. Please, do we understand? So what happens here is that this equation wouldn't work at that time, but then the capacitor would behave, because voltage is changing, the capacitor will behave like a short circuit. The capacitor will just behave like a short circuit. It will behave as if it's just a conductor there. And we've told you that whenever a short circuit condition happens, a very huge current flows. So at this time where it is charging, it obeys Ohm's law because the capacitor will act like a short circuit. And the voltage, the current that will flow suddenly into it to charge it at huge burst will be the voltage of the source times the resistor. Over here, if you don't put any line or current limiting resistor, what happens is that it is the resistance of the conductors and the cables that will be flowing through it. And for these cables, we know that their resistance is very small, around 0.05, 0.01. So what happens is that if we have, let's say we have a voltage source of 24 volts and we are dividing by 0.5, the current that flows through it will be what? 48 amperes. And this current is so huge that it can burn, the circuit itself and the wires. It can even break the circuit. So when you are charging voltages, because voltage across it cannot change suddenly, and that wide gap is there, it would behave like a short circuit because it's not actually doing anything. It won't be doing anything. So it will behave like a short circuit. And so the current that will flow through it will follow Ohm's law equation, and the current will be equivalent to the voltage at the source over the resistance of the conductor. So if the resistance is very small, your inrush current is going to be very huge. So inrush current is limited, or the amount of inrush current you have flowing through a conductor depends directly proportional on the resistance of the wire. On the resistance of the wire. Please, do we understand? Hello.
Yes, sir.
Hi.
Please, do we understand?
Yes, sir.
Yes, sir.
Yes,
Yes,
sir.
sir.
Now, look at what happens here. Look at what happens here. We said inrush current is equal to voltage over the resistance of the circuit. So, three things we can say. Three things that we can say. Number one, the higher the voltage supply. So, if voltage supply here is large, what happens? Inrush current will be large. Is that right?
Exactly.
Great. If the charging path or the resistance of the charging path is small, then what happens? Hello?
Hi.
Hi.
If the if the resistance of the
Why?
inrush is small, what happens?
The current will be small.
If the resistance is small, will the current be small?
No, sir.
No.
It will still be like depends.
It will be very big. Because look at it. It's V over R, right?
Yeah.
Yes.
So
Yes.
if R is small, what happens? Won't I be small? Won't I be big?
Yes.
Yes.
Very
Yes.
big.
Yes.
Please, you
There.
understand?
There. There.
So
Yes.
look at the problem we have. We are saying that
Hello
okay, we
there.
don't want to waste energy. We don't want to waste energy. We want to conserve energy. So we are making it, we are reducing the resistances. But if we reduce the resistances, which is good, so that we don't waste a lot of energy. If we are having short or fault current flowing, they becomes very huge. Please, do
Sir,
we
please,
understand what
someone ask
There.
come
I
again?
want to. I want to ask a question.
someone ask a question.
Yes, 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 yes.
You first said the inrush current is directly proportional to the resistance.
Yes, so I mean the level that so great. That's a very good question you're actually asking. So I meant the amount of the amount of inrush current flowing is directly proportional to um the I meant it depends on the amount of resistance you have. If you have so I should have used inversely proportional. Is that right?
Yes. Yes.
Yeah.
Yeah,
Yes.
instead of saying directly
I think
proportional.
that
Yeah.
I think that's why Efekobi said it will increase.
Yeah, I get that.
Yeah, that's why I said that.
Yes, I get that. I get that. I think what I was communicating in my mind is not what I said with my mouth. You know that thing happens. You at times you are thinking about one thing and your mouth is also saying another thing. Yeah. So
Yeah.
that
Yeah.
so that is what
Yeah.
happened. Yes. So the inrush current depends so much on the resistance of the wire. So we are saying that we don't want to waste so much energy. So we are using very good or low resistance wires. But the problem is that if you have capacitors and they have to also charge on these wires at startup because there is no voltage across it. It is taking some time to charge. It doesn't instantaneously charge. You are going to also get very large current because resistances are what small. So that's the second thing. So I said there are three things here. Higher V would give us higher I in rush. Two, lower R would give us high I Inrush. Then 3. So 3, if the capacitor is large, that means it will take more time to charge. Is that right?
Yeah.
So if we have a larger C, it means that the inrush current will stay for a longer time.
Yes.
It lasts long. Okay, so these are the 3 behaviors of capacitors at inrush or at startup. Any question before I move on? So anytime a capacitor, a device with a capacitor is starting, in fact, like I told you the last time, that is why we say that it's good you iron your clothes in bulk. It's good you do it you work, you use devices continuously. You don't start and stop them, because whenever you start and stop them, when you stop them, all these charge is released, and when you started, it has to surge. So every time you're starting and stopping things, they are always surging, and that is causing a lot of problem. And inrush current is a huge problem in industry, very very huge problem in industry, because variable frequency drives that you use to be able to regulate the speed of conveyor belt, then DC bus capacitors and servo drives, switch mode power supplies. All our power supplies that we use have something we call they are all something we call switch mode power supplies. All of them, all of them uses capacitor. Yes, is someone talking? Please, do we understand?
Yes, please.
And because they
Yes,
have
sir.
capacitance, the moment you start them up, there is inrush current. So now let's link these two things up. If you have resistors and you're starting them up, there is inrush current. You have capacitors, you're starting them up, there is inrush current. So anytime you are starting any device, there is inrush current. In fact, that is why at times if you even connect your charger to the socket, you can see some sparks. Have you observed that before?
Plenty.
Yeah, when you are plugging your charger. Me, my laptop charger like this, the moment I plug it in the socket, I'll see some sparks. Pow.
Yeah, yeah.
Yeah, it's
That's
because of the inrush current. Yeah, yeah. It's because of the inrush current. So in industry, we have to limit it. So when capacitors charge suddenly, several undesirable effects may occur. One, contact damage and arcing. Right? Because of the huge current flowing, the contacts can damage. It can burn the contact of the switches. Then some at times it will seal it. It will just seal it shut. Then fuses and circuit breakers will be tripping. It can cause voltage sag on shared supply lines, and semiconductors will have some stress, and it can also produce electromagnetic interference. Some of these questions you get them in the objectives. So now that means that the industry must solve inrush current problem, right? There are several methods, but I've given you only 2 methods. Sorry, 3 methods. In the 3 methods, what we do is this. We have already established that inrush current is equal to inrush is equal to V supply over
Wow.
R path. So, or the R charge. So what we do is that we would use 2 circuits. So this is what we do. Let's say that we have a device that works. So we have a VS here. I'm teaching you this because when you are designing your devices, at the end of the day, you'll be designing things as part of this class. When you are designing your devices, you need to be able to consider all of these in your designs. And even if you are repairing substances, right, you need to be able to consider this in your design. So let's say we have a load here. And then because because we want stable power flow, we have a large capacitor across that load. because I told you that capacitor is used to stabilize. So we have our large load here, and then there is a very large capacitor here, so that the load is powered across the capacitor, so that we don't have these spikes, instantaneous spikes up and down and those things. No, it pulls from the capacitor. So usually this is something we have a lot in the industry. Now, if the capacitor is not charged at startup because it is large, very large, it can be around thousands or 10,000s of microfarads. When we close this, and these voltages to at times are high, 48 volts or 24 volts, right? And the capacitor too is very large. That surge will last longer and it will cause a lot of harm before it starts supplying or helping the load to work. So what we do is we add a pre-charge, pre-charge resistance. You see, when you look at it, we don't want it to be that after the capacitor have started charging, have finished charging, there will be another resistance that will be wasting power. It will be consuming power and wasting it. So we don't want that to happen. So what we do is this: we will put two switches here, and we actually use this a lot in the industry. Then we have this resistor here, which will be the charge resistor. This work is just to charge. Then there will be a switch. Then we put it here. Now there is no resistor here. We don't put any resistor there. So that resistor that will charge the capacitor, we put it here. So what we do is that these two switches, they don't turn on together. It's only one that is on at any time. So when we start the device, when we turn it on, it is this switch that we will close, the R charge. So we will come and then we will close the switch. When we close this one, we open. So this is, let me call this one K charge, KC. And let me call this one K, the normal key K. So at startup, we will close KC, then open K. When we close KC and open K, the current will flow like this. The current will flow like this and charge the capacitor and come here. Is that right? So after the capacitor charges, so we will know if the capacitor is charged by monitoring the output voltage. We know that when it's fully charged, output voltage is equal to 99.33 of the Vs. So we will know. The moment it becomes fully charged, we will turn the switch off. KC. We will turn KC off. Is that right? We will turn KC off. Then we will turn KC on. K on. Please, do we understand how it works? So that when we turn KC on, the current will now flow from the load to the capacitor and back. In this loop, it doesn't flow through any resistor here. So we don't waste any energy. The total energy we have in the source is what we deliver to the capacitor. Please, is that right? Hello, are we here? Do we understand?
Yes, sir.
Yeah, yes, sir.
Yes, sir.
So we call this the pre-charge resistor. The pre-charge resistor. Now, with this method, what you can do is that you can put a large resistor in series with a capacitor. But the disadvantage is that if you increase the resistance, what it means is that it will take a long time for the capacitor to charge. But if you also reduce that charge resistance to, then it will take a short time, but then there will be huge current. And so you need to make the path of that charge capacitance very, very large so that the current would, be able to pass. Please, do we understand? Are we good?
Yes,
Yes,
sir.
sir.
All right, now let's take an example on that. So example 3.4. Example 3.4. A machine supply contains a 4,700 microfarad. So you see that here the capacitance is very large. So usually capacitances are very, very large, right? And you need to, so that it would supply the stable power that we need. So the capacitance is 4,700. And the question is asking us to find, so a machine supply contains C of 4,700 microfarads and a supply voltage of 325 volts. Calculate the initial charging current, assuming a wire resistance of 0.5 ohms. So you can do it, right? At A, we will say that I Inrush is equal to 325 over 0.5. And what do we get for this? 650 amperes. Is that right?
Yes, sir.
Yes.
Yes.
650 amperes. And this is very huge. This is a very huge current that can cause a lot of harm. A lot of harm. So we will need to use a pre-charge resistor. Now, let's just assume that we want to use a pre-charge resistor because let's say that, so B, we need to select a pre-charge resistor. We want that the time constant, we want a one-time constant to be very fast. We want it to be very fast. We want it to be around 1 ms. So that means that we have 0.01 is equal to R times 4700 micro, right? So we make R the subject. And what do we get? Yes,
47.
47.
Ohms.
So if we are using, so we are going to use 47 ohm as a pre-charge on the pre-charge path, right? Then, so what do we do? That means that I in rush would be equal to 325 over 47. And what do we have?
6.9.
6.9.
2.9.
You see, this current is better and it won't cause any harm. Is that right? What is the reduction in current from 650 to 6.9? What's the percentage reduction? Come again. Okay, so what will it be? Please, our time is quickly running. Let's pick on that. What will it be? Yes. Percentage reduction will be what?
98.93.
98.93%.
3%.
Okay, great. Now the second method we use is what we call the NTC thermistors. NTC thermistors. NTC thermistors they are actively resistors, right? They are resistors. So we call them negative temperature coefficient. Thermistor. A thermistor is a resistor whose resistance depend on temperature. Now the negative temperature coefficient means that when it is cold, you see that their resistance increase when temperature increase, right?
Yes.
That's a normal behavior of resistors. But then these ones are negative. So that means when temperature increases, their resistance what? Decreases. Right? Great. So at startup, it is cold. And because it is cold, its temperature is very high. So what happens is that because its temperature is very high, because it's cold, it naturally reduces the amount of current that flows through it because its resistance is high. Then as current passes through it, it will become warmer. And when it becomes warm, its resistance reduces. right, until it falls down to the very lowest. And so it can be negligible. It will act as if there is actually no resistance there because the temperature has increased. Then the current will be passing through it. It doesn't save a lot, it doesn't waste a lot of energy. So that one is called a passive soft start. You see, we are not actively doing anything. It's just a resistor that its behavior. We are using it to control how much inrush current flows through the circuit. Please, we understand.
Yes, sir.
Yes, sir.
Now, the only limitation is that frequent on and off cycling reduces its effectiveness because when you turn it on and off frequently, you see that it will always have to cool down and then start and all of that. And then
Yeah.
also when so there are a whole lot of consequences if you turn it on and off and it didn't really cool down before you start. We still have huge surges flowing through because if the resistor is still hot and the capacitor has fully emptied out after its 5 time constants after you turned it off and a resistor is hot, it will still pull the high inrush current we don't want it to pull unless you're able to cool that resistor. And so it's not very, very effective if you're doing frequent on and off cycling. So if you have an area where there is a frequent on and off cycling, then the best method will be to use a method one, the pre-charge resistors. Then we have the third one, which is the active soft start circuit. So we have what we call the soft starters. So you'll be hearing more of this when you go to your industry for internships, right? For internships and attachments, you'll be hearing more of this. We call it the soft start. When we say soft start, what comes to mind? Soft starters. So you see that we said I is equal to V over R. We've spoken about R, but we've not spoken about V. So soft starts works on the V. That's what it does. When the current starts, let's say the voltage is 24 volts. If you put all of that 24 volts for a 0.5 power of resistance, it's 48 amperes. It's huge. So what a soft starter does is that instead of you starting right at 24, he will start you at 2 volts. So 2 volts. So you start at 2 volts. Then he will increase you to 10, 14, gradually until you get to what? 24. So you don't instantly start at 24. It chops down the voltage and reduces it gradually until you get to 24 volts. Please, do we understand?
Yes, sir.
Yes,
Great.
sir.
Now, that is why if you go to the industry, there are some large machines, they would puff briefly after you apply power. It doesn't really start, but it pauses after. Yes, someone has a question. Yes, somebody raised his hands up. Okay, great. So we call such systems the soft starters. Is that right? Now, so in soft starting, usually we just turn the device, we pause. So the large, you can have a large machine when you start it on. It doesn't start instantaneously. It takes some time because it's doing soft starting. In fact, soft starting is the easiest and most, it's not the easiest, but the most efficient way other than all the other ones we are looking at. But then unfortunately, um, it's quite complex because you need to write a program code that will do that. You need to build advanced circuits that will be able to do that. So we usually don't like that. We go for the simpler methods, which are the passive soft starts, which uses the NTC and then the pre-charge resistors. But those are not very effective, you know. So we always like the um, passive. We like the active soft starting. So in the exams, I can ask you a question. Why does an EV Why is it that an EV will not connect the battery directly to the inverter immediately it starts? And it's all because of stop starting, because
Soft
it
start.
wants to make sure that the capacitor is fully charged before we connect it to the circuit so that we do not, have large inrush current flowing through it. So you now understand why Doomsaw has been affecting a lot of companies. Imagine you don't have any backup power supply. Then, suddenly light is taken off and you have to restart your devices, and all of these are going to surge, and you have to do soft start and have some time. So it affects your production, it affects everything because you can't just instantly start. You need to gradually ramp up current so that you do not burn your um, your equipment. Please, do we understand?
Yes, sir.
Okay,
Yes,
then
sir.
okay. In the
Yeah,
absence of any question, let's move on.
sir.
Yes.
What about stabilizers?
So you need UPS and stabilizers. Great. Uninterruptible power supplies so that you would reduce how much soft starting you have. So those are the options you have in the industry. Please, do we understand?
Yes, sir.
All right. Now
Yes,
let's talk
sir.
about another device that we usually use as mechanical engineers when it comes to electronics. In fact, these are devices you use. So this course, you see, I've already told you that in this course, my goal for you guys is that all the electronic devices you use as mechanical engineers, I will let you be aware of them because that's what basic electronics is about. So that when you go to the industry, you're already aware of some of these, and then you just go and do the practicals in the industry. And one day, if you also want to build, your components, you would be able to do it. Is that right?
Okay. Yes,
Yeah.
sir.
See. One day you're going to make the monies and you'll be eating it. Okay, great. So this is an inductor. You see, already I've established to you in a class that uh, you remember that I said whenever current flows, two things happen. Temperature increase. You remember? And what else happened? A magnetic field appears around the wire. Do you remember? Or you forgotten? Great. Excellent. Now, in capacitors, we stored the energy in electric fields as charges. But so this is in capacitors. But in inductors L, we store the energy in magnetic field. So we use something like this. Is that right? Please, do we understand?
Yes, sir.
All right, great.
Yes, sir.
So an inductor is a passive element designed to store energy in its magnetic field. So any conductor of electric current has inductive properties because any conductor, the moment current passes through it, it also produces a magnetic field. Is that right? Now, the voltage across a capacitor, sorry, an inductor. You see that we were telling you that capacitors prevent sudden change of voltage. You can't just have a voltage changing suddenly, right? You remember that we said that.
Yes.
These things are very important information you need to take note of. You need to write them down specially somewhere, right? We said that capacitors capacitors prevent sudden changes
In voltage.
in voltage. Then inductors prevent sudden changes in current. Please, do we understand?
Yes, please.
Okay, great. So capacitor, in capacitor we said current.
It's voltage.
So in capacitor we said current was equal to C dV dt. But in inductors we actually say V is equal to L di dt because current cannot change instantly. So current is an issue that we are looking at. Current is what we are concerned about. So it's voltage we'll be finding. And for capacitors, voltage is what we are concerned about. So it's current we'll be finding. So take note of these two equations. These are mirror equations, one of the other. And you would need them so much to understand how these items behave. But like we said for capacitors, an inductor, so for inductors too, the energy they store is equal to half. You see, for capacitors, EC was equal to half CV squared.
CV squared.
The same thing for an inductor, EL is equal to half LI squared. So this one you'll be getting questions on it in the objective. So learn. I want whatever bibian who am me chere wa me fam emba mo exam no mo. Na nka o ka se de ntina me ha me ho agere wo.
We are waiting for it.
I like that vim. Okay. So like we said for a capacitance, we said the capacitance of a capacitor does not depend on the circuit it is in, but it depends on the physical properties of a capacitor. So we said that C was equal to epsilon naught epsilon RAD. Similarly, for an inductor, right? For this kind of inductor, right? The wire wound inductor, L is actually equal to the number of turns times area times permeability. So this one is permissivity and this is permeability over L. So these two things, no, they are just related. Is that right? Where N is the number of turns. So just like how for capacitors, so you see capacitors and inductors are very similar. They are just an inverse or mirrors of one another. So just like how we said for capacitors, tau is equal to RC. For inductors, tau is equal to L over R. So whatever we said for an inductor, you can say the same thing for a capacitor. If an inductor is charging, its voltage output is equivalent to Vs 1 minus E negative T over tau. Then when it's discharging to E negative T over tau. The only difference is that tau is what? L
R.
over R. That's the only difference. So if you understand a capacitor, you will also understand an inductor. Now, like I'm telling you, take note of that. An inductor opposes changes in current. So whereas capacitor, you can't pass, a DC cannot pass through a capacitor. For an inductor, a DC can freely pass through it. But it opposes rapid change in current. And capacitors opposes rapid change in voltage. Please, we understand.
Yes, please.
Okay,
Yes,
great.
sir.
Now, let's look at the application of inductors in the industry. Let's look at the application of inductors in the industry. Let's take one example. There is something called an inductive kickback. let's see what happens. Let's take the behavior of an inductor, so that I will use that to explain something. Otherwise, you get confused. These things are too abstract, but you guys are brilliant. So you see, they complain. Charlie mo bin, hey, why na wo mo? Hey, why ba ni? I've been fucking. Okay, great. Excellent. Now, let's look at this question. A relay coil on a conveyor control panel has inductance L is equal to 50 mAh, right? Okay. A steady current I is equal to 200 milliamperes when energized. There is an NPN transistor switch that drives the coil to turn off in approximately 10 microseconds. So these NPN switches are very fast. They turn on very quick and they turn off very quick. So it takes 10 microseconds to turn it off. What will be the voltage spike? So look at what is happening here. We have an L, and the L is equal to L is 500. Let me take the darker one. Is Sewa on the line? Good.
Yes,
So we have
where are you?
Sewa is not on the line. So we have L to be, because I see she's on hold here. I don't know what is happening. She's been on hold for a long time.
Yeah, maybe
So you
her
guys,
network.
the network is a problem. MTN 4 there. Mo di nipa bro pa. Okay, so and the current, it carries a current I is equal to. Have you observed that always me, I like writing current in small I. It's me. That's how I like it. Right? Then it takes a duration of 10 microseconds. So let's look at the voltage that happens. The voltage across the inductor A, voltage across the inductor is equal to L di dt. You remember in senior high school, we said it's the same thing as L times changing I over changing what? T. So the current was 200 mA and it's going down to 0. And then the time change here is what? 10 microseconds. What will be the voltage? 200 milliamperes over 10 microseconds is equal to what? Times 5
500
500, yes, milli will be
megahertz.
equivalent to. What did you get? Yes, what will you get? Oh, no one
10,000
is
volts.
10,000
10,000 volts.
volts. You see how huge the voltage can be if you decide to stop current suddenly across an inductor. Please, we understand.
Yeah,
So we
yeah.
never stop current across an inductor. In fact, if you only do that if you want to burn your devices. And all these devices have inductors in them. So how do they stop? And they are stopping current instantly. So how do they do that? Now this voltage, this huge voltage, is what we call the kickback EMF, or the inductive kickback. So we call this the inductive kickback. It kicks you back. Why are you trying to turn it off? It will kick you back. So we call this voltage the inductive kickback or the back EMF. Back EMF. And it's very high. In fact, it can burn your device, it can destroy the switches, it can destroy even the transistor that switched it. It will destroy it. Please, do we understand?
Yes.
Hello? Do we understand?
Yes, sir.
Yes, sir.
Okay.
Yeah.
Okay, great. So now let's turn this practical. Let's make this practical because you guys, what we are learning is for practical. You are not learning them for theory. So what do we do? Now question B says we should find the energy stored. Let's do the energy stored before we do the practical aspect. Energy stored. B. Energy stored is half times Li squared. So when you substitute in it, what do we get? So we have
10
0.5.
millijoules.
You have what?
10 millijoules.
10 millijoules.
Yeah.
Then
Yes.
Sure.
C says, what happens to the transistor without a flyback diode? Now, he has introduced something, transistor and flyback diode. I hope you all know what a transistor is.
Sir.
Yes. You all know what a transistor is, right?
Yes, sir.
Great. No one can tell me they
Yes.
don't know
Yes.
what a transistor is. You all know what a transistor, whether you know it or not, you know it. So, so see what happens here. A transistor is a switch. Now, in the industry, we always like control systems to be turning on and off devices, right? So the switch that we use, the control systems use to turn on the devices are what we call transistors. Now, so transistors, that's what transistors are in basic terms, right? Transistors are switches, number
Yeah.
one. Now, these transistors, they switch on very low volts and they can pass very few current, just some few milliamperes. So imagine you have an AC, air conditioner, and you want, it's in a room that must cool down some operating devices. And you want to use a transistor, which is just 5 volts, to switch the AC, which is 240 volts. You see, it's not possible, right? So we've made a device called a relay. So the transistor sits here. So you have your controller. Controller is here. Then it communicates with the transistor. Then the transistor would be able to switch on a relay. Then the relay, when it switches on, the AC would work. Now, this is how the circuit looks like. This is how the circuit looks like. Please pay attention closely. Otherwise, you will get lost. So we have the microcontroller or the controller there would work through a certain resistor and would speak to this transistor. Transistors, there are two types, the NPN and the PNP, or the not pointing in. So this one that I've drawn is the not pointing in. You see the arrow is not pointing in, right? So we call that, that's how I memorize it. So not pointing in. So the not pointing in is here, like this. We will talk more about transistors very soon because you guys need to know about transistors. And this is the control signal. So what happens is that you put a relay. A relay is actually an inductor. It uses magnetic effect to close the circuit. So this is what we have. We have two switches here. So these are two switches that the AC is connected to. Then there is a conductor here. So this one is open. Now, if we turn this inductor on, so this is a relay, this guy here, this one here, this one here is a relay. So how it works is that this transistor would use small current to turn this one. So usually these guys are 12 volts. Whenever 12 volts pass through that coil here, it produces a huge magnet, and that magnet attracts this wire here so that it closes the circuit. So whenever current flows, it produces a magnetic effect that attracts this wire here, and then it closes that circuit so that current is able to flow in that AC loop. Please, do we understand? Great. But this coil here is an inductor. So if that current that is flowing from the 12 volts down here to this side, if we suddenly turn this transistor off, you see that current cannot flow again. If this transistor goes off, current cannot flow again. So and then that transistor will shut down in 10 microseconds. That means that all of that 10,000 volts, the inductor will pour it into this transistor. So what will happen to the transistor? Yes, what will happen to the transistor? Yes, talk, please talk. Festus.
It will get bent or it will explode.
It would just get bent instantaneously. Ebeshe kra. Ebeshe 1 second and back cry ebeshe. So you see that the moment you turn it off, you'll be hearing smoke. Somebody will come to your room and they'll be like, I'll go away Shapan or to say in our ocean. You'll be hearing smoke. You see. So how do we prevent this? What do we do? That is why we use something we call flyback diode. Flyback diode. So when this guy turns off, there is another device. You've heard of that device before, right? You've heard about diodes, haven't you? Senior high school, you did
Yes,
diodes.
sir.
Good. What is a
Yeah,
diode? A diode is a
Yes.
device that
device
allows
that
current to flow
allow
in
current in only one direction.
only one direction, unidirectional. So what we do is that we connect this diode in reverse. So we'll connect it here. So we'll pick our diode guy here. Then we'll connect him here like this. Like this. Please, do we understand?
Yes.
So that when this guy turns off, this guy will turn on. You know, it's in reverse bias. So if here is 12, it will never work if current is moving in this direction. If current is coming down here, it can never pass through the diode, so it won't work. It will only pass through this guy because this circuit is open. But if this circuit is because this circuit is closed. But the moment this circuit, the transistor here opens, the moment it opens now, then that negative voltage that will want to crash this will suddenly cause this one to conduct. The diode here will conduct, so it will now start flowing from the diode. It will be flowing until it decays, so that it will naturally die out. So it will not go to the transistor. It will just be flowing through the diode, flowing. Then it will naturally die out. Please, do we understand? So the diode becomes the protector. The diode is what protects the transistor. If it's not the diode, the transistor would be completely bent. So you'll be designing this circuit. In fact, you actually be designing this circuit, and so you should be able to know how to build it so that you will not fry your NPN transistor. Now, diodes are polarized devices. Polarized means that they 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 have a positive side and a negative side. I hope I've said this in class to you, right? Now,
Yes, sir.
so how will you see? You'll be wiring it yourself. So how will you see that this side is a positive and this side is a negative? The positive side, they've used a certain bar on it. So you see a certain bar here. That's a positive side. Then the transistor too is a polarized device. So with the transistor here is called the emitter, the collector. We will talk more about them in details. Here is the collector and here is the base. So usually if you take a transistor, it looks like this. It looks like the Atikopo TV. This side, and a Tikona Pose, like this. So Atikopo looks like Atikopo. You see. So if somebody tell you that your head like transistor, it means your head is having a tikopo. Okay, so this is C, and here is B, and here is E. Is that right? Please, are we here?
Yes,
Yes,
sir.
sir.
Yes, sir.
Yes.
Obviously, I've gotten a new insult to insult people. Yeah, saying now one thing. A new insult to insult people now. Okay, great. Any question before we draw the curtains for today? In fact, I couldn't really finish. So just go and solve the example in the book. I'm not going to solve them for you. Go and solve the
Okay, sir.
example 3.5 and 3.6. Go and solve them. And then
Okay, sir.
I can't finish this. Unless we meet another time and continue. The rest is plenty. I can't finish it now. If I rush through it, you won't understand. Yes, Emmanuel, you have a question, yes.
So back to the capacitors.
Yes.
Maybe you are asked to find
Hello, are you talking? Emmanuel seems to have been disconnected, unfortunately. The network is really causing a lot of harm.
I
But
also
but
have a question.
yes. Let me hear your question.
Uh, Concerning the example we solved, the first one, uh, the one we wanted a charge resistor.
Okay.
That one, the charge resistor wasn't given in the question. You tried to use a tau of 1 milliseconds to generate your own charge resistor, and I'm saying in exams will be given to us or
No, so in exams,
same.
I'll give it to you most of the time. I want you guys to, you are expert electronic engineers, so
So say okay, let's see. Uh, I use 1 millisecond and someone use maybe 2 milliseconds. You consider everyone's opinion or something like that.
Of course, that is why I am marking the script. So I don't mark with a marking scheme. No, the questions, everyone's design will be different. You just have to state why
Okay.
you are using your design. Because I'm not
Okay.
training you to be, people that will just be memorizing things. No, I'm training you so that you can design systems. And you need to understand
Oh,
why. So you need to be reasonable. You need to tell me this is why I'm choosing this. And if it's right according to the law of design we've studied all the semester, come on, why not? You have your marks.
because I think the first time I joined this one, when we were doing the tungsten, that one, you generated your own values somewhere, and I was like, who will be doing the same work? It will be given to us. That's why I asked. Thank you.
Yes,
Sir,
good. Yes,
I'm back. I had some network problems.
sorry.
Yeah. I was asking a question
Yes.
on maybe when you have asked to find the time, is there an equation you can use or
Hey, man's network is very bad. Man's network is very bad this morning. Any other question? Charlie,
Oh, sir.
you guys should give me like 15 minutes so that I'll finish timer circuit.
Okay, sir.
So that we won't come back to this next week. Next week we will start with chapter 4.
Yes, sir.
All right, thank you. Somebody raised their hands to ask a question.
Maybe it was a mistake.
Okay, great. Now let's talk about timing circuits. So, as mechanical engineers, one very common thing you would do will be to generate timing signals. So earlier we have learned that with RC circuits, you can control how fast the voltage changes with time. And if you select appropriate values of resistance and capacitors, you can be able to create predictable charging and discharging behavior based on the time. I hope we all agree to that, right?
Yes, sir.
Good. So
Yeah.
if we have, let's say, so these are timers. So I've told you that. Afia, say, why are you on the call?
Yes, sir.
I was looking at your line and you were on hold.
I was attending to something
Oh,
urgent.
okay. That's okay. I
She
told
went
you
to
you
eat.
have
Oh.
a
She went
network
to eat.
problem. Yeah, she went to eat. It's very urgent.
Yeah,
Sir,
yeah.
It's also urgent. Okay. So we said the voltage across the capacitor looks like this. Now, that tells us that we can use this to design or to design timers. But the problem with this method is that you need to charge and discharge before this capacitor will be able to work. This capacitor will be able to generate this timing sequence that you need. And in the industry, we always need time. In fact, we always need time. For instance, how does a conveyor belt knows that I need to wait for 3 seconds before I start? You remember the last example we took in class, and I said we have a welding gun that needs to hold for at least 2.5 seconds before it starts. How does that welding gun know that I have to wait for 2.5 seconds? Or take a warning flash lamp. You see, it's always flashing. How does it know how to flash repeatedly? It's going like that, bang, 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 like that. We have a lubrication system. When you go to the mining industries, then we've set it that every minute or every 5 minutes it should turn on and then spray some lubricant. You get that? So you see that we need timing, right? We really need a timing signal, right? Now this became a huge problem in the 1950s. Very, very, very huge problem. So one guy, very brilliant guy by name Kamenzind, Hans R. Kamenzind. He was working with a company called Synetics or Signetics. In 1972, he was able to design a circuit. So look at it, a circuit that was designed in 1972. Up to date, we are still using that IC. Up to date, the whole world. In fact, it is one of the most widely used IC in the industry. Because anytime you need a timer, we go back and we pick it. Right? Now, devices that are able to generate signals that repeat, we call them oscillators. So an oscillator is a circuit that produces a periodic waveform on its output with only a DC supply voltage as a required input. So the moment you just supply a voltage to it, it's able to produce, a periodic waveform for you on its output. So those devices are called oscillators. They are able to oscillate. Oscillators. They are able to oscillate. Please, do we understand? So you should know what an oscillator is. I know that you are reading in your handouts along with me. In fact, your handout, I'm almost done. Almost done. You see the way I've formatted the handout to look very nice. That's why I've taken so much time, because I don't want to give you an ugly handout. Me, I don't like ugly things. I like beautiful things. So I can't give you an ugly handout. I have to give you something that you would like to read. You read and you are so happy. You're like, oh no, this book is nice. You see, when I was in school, if I was reading a book and it was not nice, I don't read it. Mama chere me ho pa o books so can be moving from one book to the other because it's not nice. If your book is not nice, I don't read it. Okay, so yeah. So you see, these are timers, right? So an oscillator, anything that if you connect it to a power supply, it gives you a periodic waveform. So we are talking about periodic. As a matter of fact, let's take some few minutes and explain what periodic waveforms are. What is a periodic waveform? A periodic waveform has two characteristics. It has about five, but let's talk about all of them here so that you understand. All of these are in your um in your handout that I'm preparing. If your handout is sufficiently detailed to make you an expert in electronic systems, if you want to really be, but most of you, your mind is that, oh, me, I don't need to be an expert. The electrical engineers are there. You see, when you're out of school and everything is made electronic, that is when you see that you really need to be an expert to get a job. Okay, great. So this is a periodic wave. A periodic wave reveals it repeats itself after every period. Now, so it's having some behaviors. Number one, we call it a period. What a period? What is a period? A period is the time it takes for one complete waveform. So you see, when you look here, it starts, comes, go, and ends. So this is one complete waveform. Here is another complete waveform. Here is another complete waveform. Now, the time it takes to finish or to complete one waveform is what we call the period. Right? So period is equal to T1, T2, T3, T4. It's the same. You see, it's the same. Then if we say frequency is if you take 1 second, how many periods are in it? Like how many cycles are in it? How many cycles are found in 1 second? Right, for that periodic wave. So frequency is equal to 1 over period. Then the last thing is pulse width. So over here you see that it stays on, then it stays off, it goes off, right? So the pulse width is how long does it stay on? That's TW, pulse width. So the percentage of the period where it stays on is what we call duty cycle, D. Is equal to TW over T. Please, do we understand? Hello, do we understand here?
Yes, sir.
Please, please come
Yes,
again
yes.
on the TW and the duty cycle.
So the period, oh, okay. So you see, when you look at this periodic wave, you can see that for some time it's on and for some time it's off. So let me use this one. You see that for this time it's on, and for these 2 times from here to here is off. So here is when it's off, right? So the duration it takes to be on, like how long it stays when it's on, is called a um, pulse wave. So that's TW. TW is pulse wave. Pulse width. TW. Then duty cycle is a percentage of how much of the total time does it stay on. So if I say a duty cycle of 10%, it means that TW just stays on for 10% of the entire time. If it's 90%, it means that TW stays on for like 90% of the entire period. Please, do we understand?
Yes, sir.
Yes, sir.
Okay, great. Let's take some examples on this so that we can really understand what this duty cycle and pulse wave is. So I'm giving you two waves, here, two waves. Um, I have a deadline or Akosia Sewabunsu is really having a very terrible network. She comes and goes like a flash.
V1s.
What's up? Charlie, V1s oh. Obakosa. Oh. MTA, the MTM for the IA, they are shipping, but I don't blame them. Yeah, I am paying for can home be. Got Jim bribe na na the honey parging. Okay, so let's see what happens here. So these are two waveforms I've shared here, waveform 1 and waveform 2. Let's find the frequency of waveform 1. Let's do it. So what will be so first of all, what will be the period T of waveform 1? What will be T? T will be equal to what?
10 seconds.
10 milliseconds, is that right? Because the unit is
Yes,
in m.
yeah.
So
Yeah,
period is
10
what?
milliseconds.
10 milliseconds.
Okay.
What will be frequency?
0.1.
0.1 or 1 or, no, will it be 0.1? This is 1 over 10 milliseconds. So what will it
Oh,
be?
okay.
100. Excellent. So you see,
100.
if it's the objective and what you because objective no 0.1 wo. Oh, one was bro so many be no.
Yeah.
Misiamo. Some mo so mo ya bro. Tie nyina ye ho. Okay, great. Now, what will be the pulse wave? Yes. What will be pulse wave? You look
One,
at pulse wave
One
will be
on
what? One. It's just
one.
one. So pulse wave is 1 ms. Then duty cycle,
okay.
D will be equal to what? TW over T, which is equal to what? 1
1/10.
over 10. So you express it in percentage. So 10%. Let's try for 2. What is the period T?
4 milliseconds.
T
Again,
is
2 milliseconds.
Yep, 4 milliseconds.
4 milliseconds.
4. Great. So T is 4. Sorry. All the time T is capital T, not small t. So period T is what? 4 milliseconds. So what will be frequency?
400 hertz.
So frequency is 400
Hertz.
hertz.
No, 250.
What's come again? Oh, sorry,
Yeah,
250. Yes,
250.
yes, yes, 250, not 400. Hey, Guyana, who may condemn? So 250. Then what's pulse wave?
2 milliseconds.
So 2 milliseconds. So duty cycle is what?
50%.
50%. So
No.
that means that they share it exactly, right? It
Yes,
stays
yes.
on the same time and it stays off the same time. None is bigger than the other. Okay, great. So you need to understand these things to be able to use or configure a 555 timer. Now, when Hans built a 555 timer, somebody will be asking, why is it called 555 timer? It's called 555 timer because he used 5 resistors internally. So he used 3 resistors, and all those 3 resistors are 5 ohms. So 5 kilo ohms. So he just he was lazy and he just said this is going to be called a 555 timer circuit, and it's very very ubiquitous. It's used everywhere. Now, how does it look like? So this is how the 555 timer IC looks like. You need to know it. You need to know what each pin does and what to connect to each pin. Otherwise, you will get lost when it comes to the practice. Because you use 555 timer for the rest of the course. All the practical things you'll be building, you'll be using 555 timers in it. All the practical things, not even one, just a few. Because 555 timer is used everywhere in the industry. So it looks like this. So it's having 4 pins, right? 4 pins. Now, as a trick, anytime you are using an IC, so these ones are called ICs, integrated circuit, integrated circuits, ICs. Okay, so anytime you're using an IC, look out for this notch here. So you can see there is a notch there. You look carefully and you can see the notch. You see there is a notch here. Whenever you see that notch, if you position it like this, so that that notch faces north, the leftmost pin, which is here, becomes your pin number 1. then 2, 3, 4, 5, 6, 7, up to 8. So that's how we number these ICs. Is that right?
Yeah.
All right. So you will connect the voltage supply to the VCC pin. Now the 555 timer can take voltages anywhere from 5 voltage to around 20 something, 24. I think let me be sure about this so that you won't burn your device. So VCC can go, yes, 5 to 15, right? So VCC can take any voltage from 5 volts to 15 volts. Okay. Now, so these are, and then this is where the periodic signal will come out from. Pin 3 is where the periodic signal will come out from. Okay, so I will explain what these ones are very soon. But let me show you how it works. It's a little bit technical, but just follow me closely, otherwise you get lost. I don't want anyone to run away from this session this morning. Okay. Let me come up a bit. So the 555 timer is a comparator. We call it a comparator. I don't know if it's very, very important. I don't even know if it's important you know how it works, but I think it's good so that it will satisfy your curiosity and you won't think we are doing any black magic inside this box. In that way, you can also apply the principles that it uses to build your circuit in the future tomorrow. That's how so it's just circuit development is like reading, learning how to read. If you read the more you read up other people's books, the more your English becomes very good. So the more you study other people's circuits, the more you get experience in building circuits. So that's why we learn how circuits work. Okay, so this is how it looks like on the inside. So if you peel the black box, this is how a 555 timer IC look like. This is the output here. Now, let me just make it brief. This guy here is a NOT gate. So if there is an input here and it is on, let's say the input is say on, it would give an output say off. So that's how it behaves. But forget about it as if it's not there. Just forget about it. And this one is a switch. So look at what happens here. If this one is on, this switch 2 is on. So if it's on, we can get electricity flowing to ground. If this guy is off, this one too is off, so no electricity flows to ground. Is that right? Okay. Now this one here, we call it a latch, an SR latch. This SR latch, if S is on, if I say on, that means it's 5 voltage or current is connected, is flowing through it. If it is S, if it is S, the output will be off because it sets this guy kill, and then it makes this one 0. So when it puts this one high on 1, it will put this one off. So if this guy is set, here will be on and here will be off, and this does the opposite. If you press reset, set will be off and reset will be on. So observe that we are picking it from the reset. So this one, when this one is on, here will be off. Is that right? When set is on, the output at kill should be off. And if the output at kill is off, this one too will be off. And then the output will be on. And so you just follow me carefully, you will understand everything. Now, when R is on, this one is on. The output is on. Is that right? So when set is on, the output is on. right? Because when set is on, this one is off, and when this one is off, the output is on. But then when set is on, this transistor is off, so current can't flow. This one can't flow. Current can't flow here. Now look at what we do. This one here is called a comparator. It compares two signals. What does it mean? So we have plus and minus. If the plus signal is more than the minus signal, it goes off. If the minus signal is more than, sorry, it goes on. If the plus signal is more than the minus signal, it goes on. If the minus signal is more than the plus signal, it goes off. So we have connected, so you see that we have the 5, so we have 5K, 5K, 5K. Then this one too is the same thing. But then look at something here. So there are two comparators. We connected half there. So we have a voltage divider here. And this voltage divider looks like this. We have the supply voltage here. Then we have a resistor, another resistor, and another resistor. This is 5K, 5K, 5K. Then we are picking from this one. So if you do the V out here, it's going to be equal to 5 over 15 times VC. So we are going to get 1 over 3 of VCC. If we take the voltage output at this point here, similarly, we are going to get, so V output 1 is going to be 10 over 15 times VCC. And this will be equal to 2/3 VCC. Right, so what it means is that if the voltage here, so when the device starts, so look at what happens when the device starts. This is trick, that's pin 2. We connect it to a capacitor, so we calculate a capacitor here and then we connect it to it. If this capacitor is not charged, so when we start it, the capacitor is not charged, so the voltage across it is 0. So because the voltage across it is low, this guy is higher, which is 1/3 of, so if you are seeing we've connected it to 5 volts, is 1/3 of 5 volts. So this voltage, this capacitor is low. So the voltage at the positive input here becomes higher than the negative. That means it will stay on and then S will be on. When S is on, the output will be on. Is that right? Then, so the output will be on. But look at what happens. This capacitor will now be charging. When it charges and it gets to 1/3 of the input voltage of 5. So let's use 5 volts. If you are using 5 volts, 1/3 of 5 is how much? 5 over 3.
1.67.
1.6. Great. So at this side here, if we are using 5 volts, this input here is 1.6. 1.6. So as the capacitor charges and gets to 1.6, it gets a little bit above 1.6. The negatives become more than the positive input here. So it will turn off. So S will be off. And when S will be off, the output will be off. Please, we understand. So we get something like this. The output will be off. Like this. Then let's look at what happens. So when this one is off, S is off, here is on. So when here is on, this guy will turn on, right? This guy will turn on. This transistor here will turn on. And when this transistor turn on, what happens? We go to the up circuit. Now in the up circuit too, we have 2/3. So 2/3 of 5 volts is how much?
3.33.
That's 3.33. So here, the voltage is 3.33. Then we will compare it to the control, which is pin 5. And pin 5, where is pin 5? Control is connected to ground. Then, sorry, so threshold is what we compare to. Threshold is actually what we compare to. So the negative is at 3.3. The negative is at 3.3. So capacitor has risen above 1.5, so that guy is off. 1.6, so this one is off, so it's on. It has gone off. Then it's still rising. It's still rising. But then here, this capacitor is connected to this comparator here is connected to 3.3 on the negative side. So the output that it compares to is a threshold, this one. And it's still at the output of the capacitor. Right? So we are monitoring the capacitor. This capacitor, is it charging? So if it charges and then reaches 3.3 and above, then it would be more than this comparator. So it will be more than the negative. So this guy will turn on. And the moment reset turns on, Q turns on. This one turns on. So it wouldn't now be off. So this guy turned this one off. So this one will be on. Then when it's on, the output will go off. Then it will stay off. It will stay that off now. So we can see that if you're able to choose the resistor values of R1 and R2 and then the capacitor values of this, you can be able to regulate how long it stays on, here, and how long it stays off until the next cycle repeats. And this thing will just keep on charging and discharging, charging and discharging forever, as long as you've connected it to power. If you choose the capacitor and R1 and R2 right, because these ones regulate how long the pulse wave will be and what will be the duty cycle if you turn it on or you turn it off. Please, do we understand? Hello? I've lost my class. Everyone is gone.
Yes, sir.
No, yes.
Great. So no one will ask you in the exam to explain how it works, but just to satisfy your curiosity is why we are going to it. So this one is very simple. We've established that if you choose resistor values R1 and R2 and the capacitor values, you can be able to set how long your pulse wave should be and then what is the frequency that you use. So there are some formulas that we use. All you need to know is the formula. In fact, should I provide you the formulas? You
Yes.
have good minds.
Yes, sir.
No. You
Yes,
have
sir.
good minds.
Yes,
We
sir.
say,
Yes, yes, yes,
we
yes,
say.
yes.
So these are the formulas we use. It's in your handout, so you can just go and look at it. But I'm just providing the screenshots. We take one question and then we are done for this morning. Just apply that question. So you just go and do the rest for your practice so that you can solve it when you get a question in the exams. Because for me, I'll bring them. Me ma catch them say me mejije mo so. Na mama be say mejije mo so I say oh my Ghana. Papa, oh mommy pempe mo ti say wow ka jeje me so very. Okay, James. Yes. James, please, you can ask your question. Yes, James Frimpong, your answers are please ask your question. Yeah, hello, James. So yes, he's having very bad network, unfortunately. So these are the equations we use, right, in designing a 555 timer circuit. You don't need to understand how it works. All you need to know is that the equations work, and so you're using it. So this duration is what we call the T high. So here and here is called T high. And then here to here is called T low. So according to the formula, T high will be as long as this. Then T low will be as long as this. Then if you add T high and T low together, you'll get a period. Is that right? And if you add them, this is the equation. So you can 1 over that will give you this equation when you simplify it. Then this will be the duty cycle. So these are the 4 equations that you use to design a 555 timer circuit. Is that right? Let's take the example, then we close this morning. I have to attend to another thing. So I give you the circuit, and with my overtime also be on Jamaica. Oh, Ghana. This one is overtime, way overtime. You should have done 1 hour online. And now we are doing so far the call is around, it's going to 2 hours 30 minutes. No. Almost you teacher for the market you will have one to me I'll heaven there will chat you when you're kitty anyway. Hey, okay, great. Now I give you this, then I've given you R1, R2. So at times in the exams I won't even show you which one is R1, R2. But you should know. So R1 is 2.2K, right? So R1 is 2.2, R2 is 4.7. Then the capacitor is this. Now the question is that you are to find the frequency of the signal that will be generated at the output if these are the resistors. Then you have to find the frequency, the duty cycle, the high, and then the low. Easy is very simple. So you just plug them in the formula and that's all. Very, very simple. So let's find T high. T high is very, very... So T high is equal to T high. James, your hands are still up. Please let me hear your question. Yes, James. James, please, can you unmute? Maybe you're on mute. Can you kindly unmute and you talk? So the formula for T high is 0.69593 times R1 plus R2 times C capacitor. And this is going to be equal to 0.693 times R1 is what? 2.2K. 2.2K. My phone has even started misbehaving. It's tired. Then R2 is what? 4.7K. Times the capacitor, the external is what? 0.022 micro. So if you use a calculator to evaluate this, what do we get? Yes. Please, who is doing that for us? Avia.
1.05. There.
Okay, great. You've already done that. 1.0551
0.051 times 10 exponent negative 4
times 10 exponent
times 10
negative.
exponent negative 4.
So please press the ENG key. 1.051 times 10 exponent negative 4. Press the ENG key.
105.19 times 10.
So I want
105.
okay. So it's going to
mu.
be 105 mu
Yeah.
seconds. That's T high. Then we calculate T low. T low is going to be equal to 0.693. I hope you understand where the 0.693 is coming from. The time constant of the capacitor times CXT. Right, so you plug them in, then we have 0.693 times R2 is 4.7K
0.7.
times 0.022 micro. And what do we have?
Micro.
What will we get? Yes. If you are
7.16. Okay. The 71 mu.
71.
71.65.
Okay. So the total period. So what will be the total period? T, which is
T
equal
high
to
plus T low.
T high plus T low.
176 mu.
Okay. 176 mu. So what will be the frequency? 1 over the total period. Yeah, so 1 over.
5,600.
So give it to me in the
Okay,
scientific
5.68
kilo
yeah.
kilohertz. Then what will be the duty cycle? D. T high over T, right? What will it be? Yes. Yes. What do you get, please? So T high is what?
596 milli.
596
596 milli.
596%. Okay, great. Thank you very much. So that is that. And we'll be using this, we'll be using this so much in our subsequent classes. So please go and take the handouts I've given you and then solve all the questions. Follow the worked examples. Then I think I can give you some assignments here. In fact, we should have done lab 2 here, but unfortunately we don't. Our devices are not yet in. I'm having some delays from the electrical 200B, so I've not even started ordering because they're yet to give me their list. I'm hoping to get them, as soon as possible before this week ends. So you are to solve all the problems here as an assignment, right? Practice problem for week 3. All the questions here, just solve them for your assignment to be submitted in class on Monday, right? Okay, so guys,
So is
thank you
it the
very.
assignment in the chapter you shared with us?
Yes, please. The assignment, all the problems behind practice problems are all assignments from 1 to 10. 1 to 10.
Okay.
Please try your very best to not use AI. See, if you use AI and you bring it, I won't see, but it won't help you.